If the silence of the outer planets unsettles you the way it did us, don't just watch. Take action, hit like, smash subscribe, and drop a comment telling us where you're listening from, because what might happen beyond Neptune shouldn't be possible. Scientists are watching the calendar. April 3rd, 2026. Models suggest that on this date, at this precise moment, every radio telescope pointed toward the outer solar system could record the same thing. Nothing. Not interference. Not static. Not the hiss of cosmic radiation bleeding through the void. Just silence. Pure, absolute, impossible silence. For 47 minutes, according to predictive simulations run by NASA's Deep Space Network, the planets could stop singing. This isn't science fiction, this is extrapolation based on anomalies already detected. The Deep Space Network, NASA's global array of massive radio dishes scattered across 3 continents, has been tracking irregular patterns in telemetry for months. Goldstone, California, Madrid, Spain, Canberra, Australia. 3 independent stations, separated by thousands of kilometers, have all recorded intermittent dropouts from the outer solar system. Brief, unexplained, and growing more frequent. Think of it like this. Imagine every phone on Earth flickering in and out at random intervals, not because towers are failing, but because the air itself is becoming unreliable for carrying sound. That's what researchers are observing in our connection with the outer solar system. The technicians at Goldstone noticed it first in late 2024. Voyager 2, humanity's most distant ambassador, transmitted its routine heartbeat of data from the edge of interstellar space, then hesitated. Just for 3 seconds, the signal resumed. Engineers ran diagnostics. Everything checked out. The spacecraft was fine. The problem wasn't on Voyager 2. The problem was in the space between here and there. By January 2025, the dropouts were happening twice a week. By March, daily. Each blackout lasted longer than the one before. 7 seconds, 20 seconds, 91 seconds. The progression wasn't random. It followed a curve, an exponential curve. And if that curve continues its trajectory, April 3rd, 2026 is when it reaches its peak. 47 minutes of total silence. But here's what makes this more than just a technical failure. It's not just Voyager 2. The Juno spacecraft, orbiting Jupiter, experienced synchronized dropouts. New Horizons, drifting beyond Pluto, went quiet at the exact same moments. Even ground-based radio telescopes monitoring emissions from Neptune's magnetosphere detected the same interruptions. Different instruments, different distances, different targets, all silent at once. Dr. Heidi Hammel, a Neptune specialist who has spent decades studying the ice giant's atmosphere and magnetic field, reviewed the data in February 2025. Her assessment was cautious, but unsettling. We're not looking at equipment failure. We're looking at something affecting the propagation of electromagnetic waves across the outer solar system. Electromagnetic waves, radio waves, light waves, the invisible signals that carry information across the cosmos, don't just stop. They can be absorbed, reflected, scattered. But blocking them entirely across millions of kilometers simultaneously, that requires something vast, something with properties we haven't encountered before. The solar system hums with radio noise. Jupiter roars with emissions from its powerful magnetosphere. Saturn whispers in frequencies generated by its rings, interacting with charged particles. Uranus and Neptune produce fainter signals, modulated by their tilted magnetic fields. These aren't sounds in the way we hear them on Earth. They're electromagnetic oscillations converted into audio by our instruments. But the analogy holds. The planets sing, each in its own frequency, each with its own rhythm, and according to the models, they're about to stop. The timeline is precise because the pattern is mathematical. Engineers at the Deep Space Network plotted every dropout over 18 months. The intervals between blackouts decreased according to a power law, a relationship common in systems approaching critical thresholds. Earthquakes follow power laws, avalanches, stock market crashes, systems on the edge of collapse. The outer solar system, it seems, is approaching an edge. But an edge of what? NASA hasn't issued a public statement. The data remains internal, shared only among researchers with security clearance. But fragments leak. Conference presentations mention anomalous propagation delays. Technical papers reference unexpected signal attenuation in the Kuiper Belt region. The language is careful, bureaucratic. It translates roughly to, "We don't know what's happening, and we're not ready to admit it." What we do know is this: radio waves travel at the speed of light. A signal from Neptune takes approximately 4 hours to reach Earth. That's fixed, immutable. The laws of physics don't negotiate. Yet the dropouts aren't delayed by 4 hours between Neptune and Earth-based receivers. They happen simultaneously, as if the silence originates everywhere at once. Imagine a choir spread across a cathedral. The conductor raises her hand and every voice stops in perfect unison, not because each singer saw the gesture at the same time, but because the sound itself ceased to exist in the air. That's the mystery facing radio astronomers right now. Some researchers proposed solar interference. The sun constantly ejects charged particles, the solar wind, which can disrupt radio transmissions. But solar activity follows an 11-year cycle, and we're currently near solar minimum. The sun is quiet, its magnetic field is stable. There's no coronal mass ejection large enough to blanket the entire outer solar system. Others suggested a massive interstellar cloud, a wandering region of dense gas drifting between stars. The Milky Way is full of such clouds, and our solar system moves through them over millennia. But spectroscopic surveys of the local interstellar medium show no such structure approaching. The space around our solar system is, by cosmic standards, empty. A third hypothesis involves Neptune itself. Neptune is the farthest planet from the Sun, a blue giant composed mostly of methane, ice, and hydrogen, with winds that scream across its surface at 2,100 kilometers per hour, the fastest in the solar system. Its magnetic field is bizarre. Unlike Earth's, which aligns roughly with its rotation axis, Neptune's magnetic field is tilted by 47 degrees and offset from the planet's center. This creates a wobbling asymmetric magnetosphere that generates complex radio emissions. In 1989, Voyager 2 flew past Neptune and recorded these emissions for the first time. The sounds were eerie, whistles, hisses, rising tones that seemed almost biological. Scientists attributed them to plasma, interactions in Neptune's magnetosphere, charged particles spiraling along magnetic field lines and releasing energy as radio waves. But what if Neptune's magnetic field is changing? Magnetic fields aren't static. Earth's field reverses every few 100,000 years, and weaker fluctuations happen constantly. Jupiter's field strengthens and weakens on decadal timescales. Neptune, being more distant and less studied, remains largely mysterious. We have exactly one flyby's worth of magnetic data, a snapshot from 1989. Everything since has been inferred from ground-based radio observations, and those observations have been inconsistent. Starting in late 2023, the Very Large Array in New Mexico detected anomalies in Neptune's radio signature. The emissions shifted frequency. They pulsed irregularly. At times they vanished entirely for hours before resuming. By mid-2024, the pattern stabilized into something rhythmic, a pattern that repeated every 1611 hours, matching Neptune's rotation period exactly. It was as if the planet had acquired a heartbeat. Dr. Scott Bolton, principal investigator for the Juno mission orbiting Jupiter, reviewed the Neptune data alongside magnetic field measurements from Juno. His team found something unexpected. Jupiter's magnetic field showed correlated fluctuations at the exact moments Neptune's emissions changed. The planets are separated by 2.7 billion kilometers. There's no known mechanism for magnetic fields to interact across such distances in real time. Unless the interaction isn't happening in real time, unless there's a lag we haven't accounted for, or unless something else is mediating the connection. This is where speculation begins to outpace data. But the speculation isn't wild. It's grounded in physics we don't yet fully understand. Magnetic fields store energy. When they reconfigure, when field lines reconnect or collapse, That energy releases explosively. On the Sun, this process creates solar flares. On Earth, it powers auroras. On Jupiter, it accelerates particles to nearly light speed. Neptune's magnetic field, if it's undergoing reconfiguration, could be releasing energy in ways we haven't predicted. And if that energy is propagating outward, it could affect how radio waves travel through space nearby. Think of it like dropping a stone into still water. The ripples spread outward, distorting reflections, bending light rays passing through the surface. A magnetic disturbance in Neptune's magnetosphere could create ripples in the surrounding plasma environment, the thin soup of charged particles filling interplanetary space. Radio waves passing through disturbed plasma behave strangely. They slow down, they refract. In extreme cases, they reflect back entirely, but this analogy only works if the disturbance is large enough. Neptune's magnetosphere extends about 800,000 kilometers into space, a vast bubble, but tiny compared to the distance between planets. For it to affect signals from Jupiter, from Voyager 2, from New Horizons, the disturbance would need to fill most of the outer solar system. That's not a ripple, that's a wave. On February 11, 2025, an astronomer at the CHIME Observatory in Canada detected something unusual. CHIME, the Canadian Hydrogen Intensity Mapping Experiment, is designed to detect fast radio bursts from distant galaxies. It scans the entire visible sky continuously, recording any transient radio signals. Most are cosmic, pulsars, magnetars, distant cataclysms. But on that night, CHIME recorded a signal from within our own solar system. The coordinates placed it near Neptune. Declination +28 degrees, right ascension 19 hours 12 minutes. The signal lasted 9 seconds. It was polarized, structured, non-random. And it was in the ELF band, extremely low frequency, around 30 Hz. 30 Hz is far below normal astronomical radio emissions. It's the frequency range of Earth's magnetosphere, of submarine communications, of signals designed to penetrate deep into oceans or rock. It's not a frequency associated with planetary magnetic fields. CHIME's team ran the data through every filter available. They checked for terrestrial interference, satellite reflections, ionospheric effects. The signal was clean. It came from space, from the direction of Neptune, and it has never repeated. 9 seconds, 30 Hz, declination +28 degrees, right ascension 19 hours 12 minutes. We don't know what it means. We don't know if it's related to the dropouts. We don't even know if it was real. A single detection with no confirmation from other observatories always carries doubt. But the timing is hard to ignore. The signal arrived during one of the longer dropouts, a 2-minute silence that affected Voyager 2 and ground-based receivers simultaneously. It arrived as if in response. April 3, 2026 is circled on calendars at NASA, ESA, and every major observatory involved in outer solar system research. Not because anyone knows what will happen, but because the mathematics predicts convergence. The dropouts, the anomalies, the signal from Neptune, they're pieces of a pattern that's still forming. And patterns, once complete, reveal something. The outer planets have been singing since we first learned to listen. Radio emissions discovered in the 1950s, Voyager's recordings in the 1970s and 80s, decades of continuous observation. The music of the solar system, faint and strange, but always there. What if it's about to change? Key, what if the silence isn't an absence but a pause before something else begins? We'll come back to this frequency later. For now, understand this. Electromagnetic waves don't disappear without cause. Space isn't empty. It's a medium, filled with particles and fields, and disturbances in that medium propagate according to rules. Rules we think we understand. But Neptune is 4.5 billion kilometers away. It takes light 4 hours to travel that distance. And yet the silence, when it comes, will arrive everywhere at once. Stay curious. Stay watching the skies, because on April 3, 2026, we may finally hear what the void has been trying to say. To understand why the predicted silence matters, we need to understand how we listen to the cosmos in the first place. Radio astronomy isn't like optical astronomy. You can't point a radio telescope at Neptune and see the planet the way Hubble captures images of galaxies. Radio waves are invisible, low energy, and maddeningly faint. Detecting them requires enormous dishes, sensitive receivers, and patience measured in hours. The Deep Space Network is humanity's ear pressed against the solar system. 3 stations, positioned roughly 120 degrees apart around Earth's equator, ensure that at least one is always facing any spacecraft or distant object. As Earth rotates, the stations hand off tracking responsibilities like relay runners passing a baton. Goldstone watches Voyager 2 for 8 hours, then Madrid takes over, then Canberra. Continuous coverage, no gaps. Each station uses a 70-meter dish, a structure so large it takes 5 minutes to rotate from one target to another. The surface is precise to within millimeters. Any imperfection scatters incoming signals, reducing sensitivity. Think of it like a mirror. Scratch the surface and the reflection blurs. These dishes are polished to near perfection, engineered to focus radio waves from billions of kilometers away onto a receiver the size of a briefcase. That receiver is cooled to near absolute zero. Why? Because heat generates noise. At room temperature, atoms jiggle and vibrate, creating random electromagnetic fluctuations. Static. Cool the receiver to a few degrees above absolute zero, and the atoms barely move. The static drops. The signal stands out. Even then, the signal is unimaginably weak. Voyager 2 transmits with a 23-watt radio, less power than a refrigerator light bulb. By the time that signal crosses the solar system, spreading outward, like ripples from a pebble dropped in an ocean, it arrives at Earth carrying less energy than a snowflake falling on your hand. Yet we detect it. We decode it. We extract science. This is engineering at its limit. A single miscalculation, a single component failure, and the signal vanishes into noise. The fact that the Deep Space Network has maintained continuous contact with spacecraft for decades is a testament to human precision, which makes the dropouts even stranger. When Voyager 2's signal disappeared for 3 seconds in late 2024, engineers assumed hardware failure. They ran diagnostics on the spacecraft's transmitter. They checked the DSN receivers. They recalibrated the atomic clocks that synchronized data reception. Everything was nominal. The spacecraft was transmitting, the receivers were listening. The signal simply wasn't arriving. Radio waves don't take detours. They travel in straight lines at light speed unless something bends or absorbs them. Interstellar dust can scatter high-frequency light, which is why distant stars appear reddish, but radio waves, with their long wavelengths, slip past dust grains like ocean waves rolling past pebbles. They're resilient, reliable, until they're not. The 3-second dropout was logged as an anomaly, a statistical outlier. Radio astronomy is full of them. Cosmic rays strike receivers, software glitches introduce errors, thunderstorms on Earth generate interference. One anomaly isn't a pattern, but then it happened, again and again. By March 2025, engineers at Goldstone began tracking the dropouts systematically. They created a database, timestamp, duration, affected spacecraft, atmospheric conditions, solar activity. They looked for correlations. Solar flares, no correlation. The dropouts occurred regardless of solar weather. Atmospheric interference, no correlation. Clear nights and stormy nights showed identical dropout rates. Spacecraft orientation, no correlation. Voyager 2's antenna always points toward Earth. The dropout rate didn't change. The only correlation they found was timing. The dropouts occurred simultaneously across multiple spacecraft and ground-based observations. Voyager 2 near the heliopause, New Horizons beyond Pluto, Juno at Jupiter, ground telescopes monitoring Neptune's magnetosphere, all silent at the same moments. That shouldn't be possible. Radio waves from Voyager 2 take over 22 hours to reach Earth. Waves from New Horizons take roughly 7 hours. Waves from Juno take 45 minutes. If the dropouts were caused by something happening at the source, a change in the spacecraft or planet transmitting the signal, Earth-based receivers would detect them hours apart, staggered by light travel time. But they weren't staggered. They were synchronous, which means the dropout isn't happening at the source. It's happening in the space between the source and Earth, and it's happening everywhere simultaneously, or at least across a volume of space so large that light travel delays become negligible. Imagine turning off all the lights in a city at once, not by cutting power to each building individually, but by flipping a single master switch. The dropouts suggest something like that, a master switch for electromagnetic propagation across the outer solar system. Physics doesn't offer many candidates for such a mechanism. One possibility, a massive increase in plasma density. Space isn't empty. It's filled with charged particles from the solar wind, thinly spread but constantly present. Radio waves passing through plasma slow down slightly, and if the plasma becomes dense enough, the waves can be absorbed entirely. But creating a sudden, temporary surge in plasma density across billions of cubic kilometers requires an event orders of magnitude larger than any observed solar storm. Another possibility, gravitational lensing, but in reverse. Einstein's general relativity predicts that massive objects bend space-time, and light, including radio waves, follows those curves. A black hole, for instance, bends light so severely it creates a shadow, a region where no light escapes. Could something be bending radio waves away from Earth? Possibly, but the object would need to be incredibly massive and perfectly positioned between Earth and every affected spacecraft. And it would need to move, explaining why the dropouts are temporary. No known object fits that description. A third possibility, quantum effects. At extremely small scales, particles don't behave deterministically. They exist in superposition, tunneling through barriers, entangling across distances. Could quantum effects, somehow amplified to macroscopic scales, affect radio wave propagation? The idea sounds absurd. Quantum mechanics governs atoms and photons, not interplanetary signals. But in the early universe, quantum fluctuations seeded the formation of galaxies. Scale matters. None of these explanations are satisfying. Each requires assumptions that strain credibility, which leaves researchers in an uncomfortable position. Either the data is wrong, or our understanding of how radio waves propagate through space is incomplete. The data has been checked, rechecked, verified across independent systems. The error bars are tight, the dropouts are real. So we return to Neptune. Ground-based radio telescopes have monitored Neptune's emissions for decades. The planet's magnetosphere generates radio waves through a process called cyclotron radiation. Charged particles spiral along magnetic field lines, accelerating and emitting energy at specific frequencies. The emissions vary with Neptune's rotation, creating a lighthouse effect, brighter when the magnetic pole faces Earth, dimmer when it rotates away. This pattern should be regular. Neptune rotates every 16.11 hours. The emissions should pulse with the same period, predictable as a metronome. But starting in late 2023, the rhythm changed. The pulses became irregular. Sometimes they arrived early, sometimes late. By mid-2024, the irregularity stabilized into a new pattern, a double pulse, repeating every 16 to 11 hours, but with a slight asymmetry. One pulse strong, one pulse weak, like a heartbeat with a murmur. Dr. Heidi Hamel, reviewing the data, noted that such asymmetry suggested a structural change in Neptune's magnetosphere. Magnetic fields reconfigure constantly on Earth, driven by convection in the molten iron core. Neptune's field, generated by convection in an ocean of liquid metallic hydrogen deep inside the planet, should be even more dynamic. A shift in the internal flow patterns could twist the field into a new configuration. But why now? Neptune has existed for 4.5 billion years. Its internal dynamics have operated continuously since formation. Random fluctuations happen, but coinciding with the dropouts, that's harder to dismiss. The signal detected by CHIME on February 11, 2025, adds another layer of mystery. 30 Hertz. That's not a frequency produced by cyclotron radiation. It's too low, too structured. Natural radio emissions from planets tend to fall in the kilohertz to megahertz range, thousands to millions of cycles per second. 30 hertz is almost infrasound, at the very edge of human hearing if converted to audio. It's also the natural resonance frequency of Earth's ionosphere. The Schumann resonances, standing electromagnetic waves trapped between Earth's surface and the ionosphere, cluster around 7.83 Hz, 14.3 Hz, and higher harmonics. 30 Hz fits that pattern. Could Neptune have similar resonances? Its atmosphere is thick, layered, charged by auroras at the poles. But the geometry is different. Earth's ionosphere forms a neat spherical shell. Neptune's magnetosphere is tilted, offset, asymmetric. The resonances, if they exist, wouldn't match Earth's, unless something else is resonating. We'll come back to this frequency later. For now, consider this. The Deep Space Network was built to listen to spacecraft, but it also listens to planets. And in the months leading up to April 3rd, 2026, the distinction has blurred. Voyager 2 transmits intentionally. Neptune does not, yet both are sending signals. Both are going silent. The question isn't just what's blocking the signals. The question is, what's coordinating the blockage? And the answer, if the models are correct, may reveal itself in 47 minutes of perfect silence. Stay locked in. We're only beginning to understand what the outer solar system is trying to tell us. By the time researchers recognized the dropouts as a pattern rather than isolated failures, 6 months had already passed. Pattern recognition is harder than it sounds. Human brains excel at finding patterns, sometimes too well, seeing faces in clouds, meaning in randomness. Scientists trained to resist this instinct, demanding statistical significance before declaring a pattern real. But this caution has a cost. It delays recognition of genuine anomalies. The first 3-second dropout in late 2024 was filed under transient interference. The second, a week later, was logged as possible hardware glitch. By the 5th occurrence, engineers began comparing notes. By the 10th, they opened an investigation. By the 20th, the investigation escalated to NASA headquarters. The turning point came in December 2024, when a graduate student at MIT, working on an unrelated project analyzing Voyager telemetry, plotted all documented dropouts on a single timeline. The graph revealed something shocking. The intervals between dropouts were decreasing according to a power law. A power law is a mathematical relationship where one quantity varies as a power of another. Earthquakes follow power laws. Small quakes are common, large quakes are rare, and the frequency decreases predictably with magnitude. Avalanches, forest fires, stock market crashes, all obey power laws. They're signatures of systems approaching critical transitions. The dropout intervals fit this pattern perfectly. The first dropout lasted 3 seconds, occurring after months of normal operation. The second occurred a week later. The third, 4 days later. The fourth, 2 days. The gaps were shrinking, accelerating toward a point where the dropouts would become continuous. Extrapolating the curve forward, the student calculated that by April 2026, the system would reach criticality, a single sustained dropout lasting 47 minutes. The calculation was reviewed by faculty advisors. They checked the math. They ran Monte Carlo simulations, testing whether random fluctuations could produce a similar pattern. The probability was vanishingly small, less than 1 in 10,000. The pattern was real. NASA convened a closed-door meeting in January 2025. Representatives from the Deep Space Network, Jet Propulsion Laboratory, and the Applied Physics Laboratory attended. The agenda: determine whether the dropouts posed a risk to mission operations and identify possible causes. The conclusion: no immediate risk. Spacecraft are designed to operate autonomously during communication blackouts. Voyager 2, for instance, can function for weeks without ground contact, executing pre-programmed commands stored in onboard memory. A 47-minute silence, while unprecedented, wouldn't endanger the mission. But the cause remained unknown. and unknown causes are uncomfortable in aerospace engineering. The meeting produced 3 working hypotheses. Hypothesis 1, solar minimum effects. The Sun's activity follows an 11-year cycle, alternating between solar maximum, high activity, many sunspots, frequent flares, and solar minimum, quiet, few sunspots, weak magnetic field. During solar minimum, the Sun's magnetic field weakens, allowing more cosmic rays to penetrate the inner solar system. Cosmic rays ionize the interplanetary medium, increasing plasma density, which could theoretically affect radio wave propagation. But this hypothesis had problems. Cosmic ray flux had been measured continuously since the 1950s. The current solar minimum was unremarkable. Cosmic ray levels were high, yes, but not anomalously so. And cosmic rays affect radio propagation uniformly. They don't create sharp, synchronous dropouts. Hypothesis 2, interstellar medium interaction. The solar system is moving through the local interstellar cloud, a region of slightly denser gas and dust. Voyager 1 crossed the heliopause, the boundary where the solar wind meets interstellar space, in 2012. Voyager 2 followed in 2018. Both spacecraft detected changes in plasma density and magnetic field strength beyond the heliopause. Perhaps turbulence in the interstellar medium was propagating inward, affecting radio wave propagation throughout the outer solar system. This hypothesis was more plausible, but still incomplete. Interstellar turbulence operates on timescales of thousands of years, not months, and it wouldn't explain the power law timing of the dropouts. Hypothesis 3, magnetospheric reconfiguration. Neptune's magnetic field, tilted and offset, generates a complex magnetosphere. If the field were reconfiguring, shifting pole positions, changing strength, it could alter the plasma environment across a vast region. Charged particles trapped in Neptune's magnetosphere could be released, creating waves of enhanced plasma density that propagate outward, temporarily blocking radio waves. This was the leading hypothesis. It explained the timing, gradual build-up toward a critical event. It explained the synchronicity. A wave propagating at near light speed could affect multiple locations nearly simultaneously. And it connected to observable data, the changing rhythm of Neptune's radio emissions. But it also required something unprecedented. Neptune's magnetosphere extends roughly 800,000 kilometers into space, a fraction of the distance between Neptune and Uranus, let alone Neptune and Jupiter. For a magnetospheric event to affect the entire outer solar system, the scale would be enormous. Not just a reconfiguration, a transformation. The meeting ended without consensus. More data was needed, more observations, and time. By March 2025, the dropouts were occurring daily, 15 seconds, 30 seconds, 90 seconds. Each blackout erased a small chunk of telemetry from Voyager 2, New Horizons, and Juno. The data gaps were frustrating, but not catastrophic. Spacecraft telemetry is redundant. Critical information is transmitted multiple times, and engineers can reconstruct missing sections from context. But the gaps were widening, and the pattern was clear. April 3, 2026, 1447 UTC. Around this time, a second anomaly emerged, seemingly unrelated but eerily parallel. Radio telescopes monitoring Jupiter began detecting irregularities in the planet's decametric emissions. Powerful radio bursts generated by interactions between Jupiter's magnetic field and its moon Io. These emissions are among the strongest natural radio sources in the solar system, loud enough to be detected by amateur radio enthusiasts on Earth using simple antennas. Jupiter's emissions are driven by Io's volcanic activity. Io orbits deep within Jupiter's magnetosphere, spewing sulfur and oxygen into space. These ions get caught in Jupiter's magnetic field, spiraling along field lines and crashing into the planet's atmosphere near the poles, generating auroras and radio waves. The process is well understood, predictable. Except in early 2025, the emissions started flickering, not dimming gradually, but cutting out abruptly for seconds at a time, then resuming at full strength. The flickers coincided, loosely, not perfectly, with the dropout events affecting spacecraft telemetry. Dr. Scott Bolton, analyzing Juno's magnetic field data, noticed something else. Jupiter's field was wobbling. Not the large-scale structure, but fine details. Small-scale fluctuations in field strength and direction, oscillating at frequencies that matched the flicker rate of the radio emissions. Magnetic fields don't wobble randomly. They respond to changes in their source. Jupiter's field is generated by convection in its liquid metallic hydrogen interior, driven by the planet's rotation and internal heat. For the field to wobble externally, something internal must be changing, or something external is pushing on it. Bolton's team ran simulations. They modeled how external magnetic disturbances, like those from the solar wind, might perturb Jupiter's magnetosphere. The results showed minor wobbles, but nothing matching the observed amplitude. The external push would need to be far stronger than anything the Sun produces, unless it wasn't coming from the Sun. Magnetic fields interact. Two bar magnets placed near each other exert forces on one another, aligning or repelling depending on pole orientation. Planetary magnetic fields can interact similarly, though the distances involved make the forces negligible under normal conditions. Jupiter and Neptune are separated by 2.7 billion kilometers. Their magnetic fields, while vast, don't reach that far. They shouldn't influence each other. But what if Neptune's field was extending farther than expected? What if the reconfiguration wasn't just internal, but external? A ballooning of the magnetosphere outward, driven by an internal event so powerful it reshaped the surrounding space. This idea stretched plausibility. It required energy, enormous energy, the kind of energy associated with magnetic reconnection events where field lines snap and reconfigure explosively, releasing stored magnetic energy in an instant. On the Sun, reconnection drives solar flares, releasing 10 to 25 joules in minutes, equivalent to millions of nuclear bombs. Neptune is smaller than the Sun, its magnetic field weaker. But if reconnection were happening on a planetary scale, the energy released could still be staggering. Enough to accelerate particles, enough to generate shock waves in the surrounding plasma, enough perhaps to affect radio wave propagation across billions of kilometers. The mathematics were speculative, but not impossible. Reconnection events on Neptune could generate fast-mode magnetosonic waves, pressure waves in plasma that travel at speeds approaching the Alfvén speed, determined by magnetic field strength and plasma density. In the tenuous plasma of the outer solar system, Alfvén speeds can reach hundreds of kilometers per second. A wave traveling at 500 kilometers per second would cross the distance from Neptune to Jupiter in about 60 days. The first observed dropout occurred in late 2024. 60 days earlier places the event in September or October 2024, a period when Neptune was poorly positioned for ground-based observation, behind the Sun from Earth's perspective. If something happened then, a magnetic reconnection event, a magnetospheric eruption, we might have missed it entirely. The first clue would have been the wave's arrival at Jupiter months later, followed by its gradual approach toward the inner solar system. By April 2026, the wave would reach Earth's orbit, and everything in its path would go silent. This is speculation, but it's grounded in physics. Magnetosonic waves exist. Reconnection events happen. The timing fits. The question is whether Neptune's magnetosphere is capable of producing such an event, and whether we'd recognize it if it did. We'll come back to this question later. For now, understand that patterns in data don't lie. They point toward causes, even if those causes defy expectations. The dropouts are real. The acceleration is real. April 3rd, 2026 is approaching, and the outer planets are trying to tell us something before they fall silent. Stay watching. We're not done listening yet. Observation is the backbone of astronomy. For centuries, astronomers have watched, waited, recorded. Patterns emerge not from single observations, but from thousands compiled over decades. The transit of Venus, the precession of Mercury, the moons of Jupiter. Each discovery required patience. but patience has limits when the timeline is finite. By February 2026, every major radio observatory on Earth had April 3rd marked on their schedules. The Very Large Array in New Mexico, the Arecibo Observatory in Puerto Rico, recently restored after its 2020 collapse, the Chime Telescope in Canada, the Parkes Observatory in Australia, the LOFAR Array across Europe, all coordinated to observe the outer solar system simultaneously during the predicted 47-minute window. This was unprecedented. Radio telescopes are in high demand, and observing time is allocated months in advance through competitive proposals. To clear schedules across multiple facilities required intervention from funding agencies, national science foundations, and diplomatic channels. The message was clear. Whatever happens on April 3rd, we need to see it from every angle. The plan was simple: continuous observation of Neptune, Uranus, Jupiter, and the regions surrounding each planet. Multiple frequencies, from ELF, extremely low frequency, to decametric bands. Polarization measurements to detect magnetic field orientations. Spectroscopy to identify plasma composition. And crucially, time synchronization to nanosecond precision across all observatories. If the silence was a wave, they would triangulate its origin. If it was a field reconfiguration, they would map its structure. If it was something else entirely, something not yet imagined, the data would at least provide constraints. NASA's Deep Space Network prepared differently. Their concern wasn't scientific discovery, but operational continuity. Losing contact with spacecraft for 47 minutes was manageable, but only if the spacecraft were in stable configurations. Voyager 2's trajectory was locked. New Horizons was in hibernation mode. Juno orbited Jupiter on autopilot. But other missions, active rovers on Mars, orbiters studying Venus, the Parker solar probe diving near the Sun, all required careful timing to ensure the blackout didn't occur during critical maneuvers. Mission planners adjusted schedules. Commands were uploaded early. Spacecraft were instructed to record telemetry internally during the blackout and transmit it afterward. Redundancy was built into every system. If April 3rd passed without incident, the adjustments would be unnecessary. If the prediction held true, they would ensure no data was lost. But data, in this case, was secondary. The real question was, what would the silence reveal? Silence in astronomy is informative. When a star suddenly stops emitting light, it tells us the star has died, collapsed into a black hole, or exploded as a supernova. When a pulsar's regular ticking ceases, it suggests the neutron star has stopped rotating, or its beam no longer sweeps across Earth. Absence of signal is still information. The predicted silence over the outer solar system would be the same. If radio waves stop propagating, the reason matters. Is it absorption, reflection, refraction into directions where Earth-based receivers can't detect them? Each mechanism leaves fingerprints. Absorption would require a medium dense enough to capture photons. Plasma can do this, but only if its density exceeds certain thresholds. Measuring how quickly signals resume after the blackout, whether they fade in gradually or snap back instantly, would reveal whether absorption is occurring. Reflection would require a surface or boundary, a sharp transition in plasma density or magnetic field strength. Radio waves encountering such boundaries behave like light hitting a mirror, bouncing back toward their source. If reflection is occurring, spacecraft might detect their own transmissions echoing back, delayed by the round-trip travel time. Refraction bends waves without blocking them. A lens refracts light, focusing or dispersing it. Plasma, with varying density, acts like a lens for radio waves. If the blackout is refractive, signals might not disappear entirely. They might simply arrive from unexpected directions, bent by plasma structures we can't see directly. Each scenario predicts different observational signatures, and April 3rd would reveal which, if any, applies. But there's a fourth possibility, quieter and more unsettling: coherence. Coherence, in physics, means waves oscillating in sync, peaks aligning with peaks, troughs with troughs. Lasers are coherent, sunlight is not. Coherent waves interfere constructively, amplifying each other. Incoherent waves interfere destructively, cancelling out. Radio emissions from planets are typically incoherent. They're generated by countless charged particles moving chaotically, each producing a tiny wave with random phase. The sum is noise, structured noise, carrying information, but fundamentally random. Incoherent emissions can't be blocked by interference. There's nothing to interfere with, unless something imposes coherence. Imagine a stadium full of people talking simultaneously. The sound is loud but unintelligible. Now imagine someone plays a single note on a loudspeaker and everyone stops talking to listen. The silence isn't absorption or reflection, it's synchronization. The crowd becomes coherent, silent together. Could something similar happen to planetary radio emissions? Could an external signal, a pulse, a field, a wave, impose coherence on the charged particles generating radio noise, causing them to oscillate in sync and then cancel out? It sounds fantastical, but coherence effects happen in nature. Bose-Einstein condensates are clouds of atoms cooled until they all occupy the same quantum state, behaving as a single coherent entity. Superconductors exhibit coherent electron flow with zero resistance. The mechanisms are quantum, operating at atomic scales. But the principle isn't limited by scale. If a large-scale coherence mechanism existed, some way to synchronize particles across vast distances, it could theoretically silence radio emissions without blocking them. The waves would still exist, but interfere destructively, summing to zero. This is deep speculation, but it connects to the signal detected by CHIME in February 2025. 30 Hz, a frequency that doesn't belong to planetary emissions, a frequency that suggests resonance. Resonance is nature's way of imposing coherence. Push a swing at its natural frequency, and it amplifies. Push at the wrong frequency and nothing happens. Every system has a natural frequency: guitar strings, wine glasses, bridges, even planets. Neptune's internal structure, layers of hydrogen, helium, methane, and exotic ices under extreme pressure, has mechanical resonance modes. Seismic waves, if they existed on Neptune, and they might, driven by convection or gravitational tides, would oscillate at specific frequencies determined by the planet's size and composition. 30 Hertz is within the plausible range for a low-order seismic mode on an ice giant. If Neptune were oscillating, if its interior were vibrating at 30 Hz, that vibration could couple to the magnetosphere, modulating the magnetic field rhythmically, and a modulated magnetic field would affect charged particles in the surrounding plasma, imposing a rhythm on their motion. A rhythm means coherence, and coherence, taken to an extreme, could mean silence. This is hypothesis stacked on hypothesis, speculation wrapped in speculation, but it fits the data. The changing rhythm of Neptune's radio emissions, the 30 Hz signal, the power law progression of dropouts, all consistent with a system building toward resonance. And resonance, once achieved, can be catastrophic. Bridges collapse when wind matches their natural frequency. Wine glasses shatter when sound waves resonate with their structure. What happens when a planet resonates? We don't know. We've never observed it. But on April 3, 2026, we might. The vigil isn't just scientific curiosity. It's preparation for something we don't yet understand. Observatories are ready. Spacecraft are configured. Engineers and scientists are on call, waiting. The countdown has begun. 47 minutes, that's all. 47 minutes of silence, predicted by mathematics, inferred from months of anomalies, pointing toward a moment when the outer solar system might reveal something fundamental about how electromagnetic waves propagate through space. Or it might reveal nothing. The silence might pass without consequence. The dropouts might stop afterward, the pattern broken. We'd be left with data, questions, and no answers. But the alternative, that the silence is a beginning, not an ending, is what keeps astronomers awake at night. We'll return to this moment later. For now, preparations continue. Observations are scheduled, data pipelines are tested, and on every telescope, every receiver, every screen. The same coordinates are locked in. Neptune, declination plus 28 degree. Right ascension 1912 Mers, the place where the signal came from. The place where perhaps something is waiting to be heard. Stay with us. The vigil has only just begun. Human beings are storytellers. We see patterns, draw connections, construct narratives. It's an evolutionary advantage. Recognizing that rustling grass might mean a predator kept our ancestors alive, but the same instinct that protects us can mislead us. We see faces in clouds, meaning in randomness, conspiracies in coincidence. The challenge always is distinguishing real patterns from imagined ones. By early 2026, the predicted April 3rd event had leaked beyond scientific circles. Not officially, NASA had issued no public statements, but whispers spread through online forums, amateur astronomy communities, and social media. Screenshots of technical papers, second-hand accounts from observatory staff. Speculation piled on speculation, and with it came theories, some grounded in physics, others less so. The most common narrative was simple. The silence would be a message, not from Neptune, but from something near Neptune. An intelligence, a probe, a signal deliberately timed to coincide with a moment when humanity would be listening. The logic went like this. If an advanced civilization wanted to contact us, they wouldn't transmit randomly. They'd wait for a moment when we'd be paying attention, a moment of maximum observational focus. And April 3rd, with every major telescope aimed at the outer solar system, fit that description perfectly. The counter-argument was equally simple. We're paying attention because we predicted the event. We created the moment. Any intelligence sophisticated enough to time a signal would also be sophisticated enough to transmit continuously, making timing irrelevant. Waiting for April 3rd would be like waiting for someone to look out their window before waving. Pointless when you could just knock on the door. But logic rarely stops speculation. Another theory suggested the silence wasn't external but internal, a solar system-wide defense mechanism. Proponents argued that Earth's magnetosphere protects us from solar radiation, and perhaps the solar system has a larger-scale equivalent, a boundary or field that activates in response to external threats. The dropouts, in this view, were warning signs. The magnetosphere was reconfiguring, preparing for something arriving from interstellar space. This theory had a kernel of plausibility. The heliopause, the boundary where the solar wind meets the interstellar medium, does act as a shield, deflecting some cosmic rays and interstellar particles. Voyager 1 and 2, after crossing the heliopause, detected changes in particle flux and magnetic field orientation, consistent with a boundary layer. But boundaries don't activate. They exist passively, shaped by the balance between outward solar wind pressure and inward interstellar pressure. Changing that balance requires changing the sun's output or the interstellar medium's density. Neither was occurring. A third theory, darker and more fatalistic, suggested the dropouts signaled a breakdown in physical law. Electromagnetic theory, the foundation of radio astronomy, is based on Maxwell's equations, mathematical relationships describing how electric and magnetic fields interact. Those equations have been tested exhaustively for over a century. They predict radio wave propagation with extraordinary accuracy. But what if they're approximations? What if, under conditions we've never encountered, the equations break down? The dropouts in this view were evidence that something in the outer solar system was creating conditions where Maxwell's equations no longer applied. Not a violation of physics, but a revelation that our physics is incomplete. This theory was the hardest to dismiss outright. Physics has a history of surprises. Newtonian mechanics worked perfectly until we examined objects moving near light speed, and relativity replaced it. Quantum mechanics emerged when classical physics failed to explain atomic behavior. Each revolution didn't erase the old framework. It revealed limits, boundaries beyond which new rules apply. Could the outer solar system, far from the sun's influence, cold and dark and strange, be revealing such a boundary? The scientific community treated these theories with caution, not dismissal. Dismissing ideas without evidence is as unscientific as accepting them without evidence. But caution. Extraordinary claims require extraordinary evidence, and so far the evidence was suggestive but not conclusive. Dr. Heidi Hammel, speaking at a conference in February 2026, put it this way: "We're observing something unusual. That's undeniable, but unusual doesn't mean impossible or inexplicable. Nature surprises us constantly. Our job is to gather data, test hypotheses, and avoid jumping to conclusions." April 3rd will give us that data. Her words were measured, professional, calibrated to avoid both panic and false certainty. But even she acknowledged the timing was unsettling, because it wasn't just the dropouts. In January 2026, seismologists detected an unusual pattern in Earth's ambient seismic noise. Seismic noise is the constant, low-level vibration of the planet, generated by ocean waves, wind, human activity, and tectonic creep. It's always present, a background hum that seismometers filter out when searching for earthquakes. But the hum had changed. Specifically, a narrow frequency band around 0.029 Hz, a period of roughly 6 minutes, had amplified slightly over several weeks, then faded. The amplification was minor, barely detectable, but it appeared in seismic records globally. Not a localized phenomenon, a planetary one. Seismologists had no explanation. Ocean wave patterns, the usual driver of seismic noise, hadn't changed. Atmospheric pressure was normal. There were no major earthquakes during the period. The signal remained a mystery. Then someone noticed 0.29 Hz is close to one of Earth's free oscillation modes. Free oscillations are the planet's natural vibrational frequencies, excited when large earthquakes release energy into the entire globe. The vibrations are slow, periods of minutes to hours, and they decay over days. But they're predictable, tied to Earth's size and internal structure. The January amplification matched a free oscillation mode. But no earthquake had occurred, no impact, no volcanic eruption, nothing energetic enough to excite the mode, unless the energy came from outside. Gravitational waves, ripples in space-time generated by colliding black holes or neutron stars, can shake planets. The effect is tiny, detectable only by the most sensitive instruments. But if a gravitational wave passed through the solar system, it would vibrate every planet simultaneously, each ringing at its natural frequency. Gravitational wave detectors, LIGO in the United States, Virgo in Europe, CAGRA in Japan, found nothing. No black hole collisions, no neutron star mergers, no gravitational waves, yet Earth had rung like a bell. And the timing, January 2026, weeks before the predicted April 3rd event, was hard to ignore. Correlation isn't causation. This is the first rule of data analysis. Two events occurring near each other in time don't necessarily share a cause. Coincidences happen. The universe is large, and rare events occur constantly somewhere. But when coincidences accumulate, they stop feeling coincidental. Neptune's changing radio emissions, the dropout pattern accelerating toward April 3rd, Jupiter's wobbling magnetic field, Earth's unexplained seismic hum, the 30 Hz signal from declination plus 128 degrams, right ascension 19H12 emitters, each individually explainable as random fluctuation. Together, they suggested coordination. Conspiracy theories thrive on coordination without clear mechanism. Someone or something is orchestrating events behind the scenes. The lack of visible connection becomes evidence of hidden connection. It's a trap, a cognitive bias that misleads more often than it enlightens. But science isn't immune to the trap. When data points align too neatly, when timing seems too perfect, the question shifts from, is there a connection, to what kind of connection? And that question leads to uncomfortable places. If Neptune's magnetosphere is reconfiguring, and that reconfiguration is generating waves propagating through the solar system, Those waves would carry energy. Energy interacts with matter. A wave passing through Jupiter's magnetosphere would push on charged particles, causing the wobbles observed by Juno. A wave passing near Earth could couple to the planet's magnetic field, inducing currents in the mantle that excite seismic modes. This is speculative but consistent with physics. Magneto-hydrodynamic waves, waves in magnetized plasma, can travel vast distances, transferring energy from one region to another. The Sun generates such waves continuously, and they propagate outward with the solar wind. A similar wave originating at Neptune could, in principle, affect the entire solar system. But the energy required is staggering. Neptune's magnetosphere stores energy in its magnetic field, but releasing that energy fast enough to generate system-wide effects would require a catastrophic event. Something like a planetary-scale magnetic storm, far more powerful than anything observed on Earth or Jupiter. Is Neptune capable of such an event? We don't know. We've observed the planet for decades, but always from afar. Voyager 2's flyby in 1989 provided a snapshot, a single pass through a dynamic system. Everything since has been inference, interpretation, extrapolation. Maybe Neptune has storms we've never seen. Maybe its interior is more active than models predict. Maybe the magnetic field undergoes periodic reversals, and we've simply never been watching when one occurred. Or maybe something else is happening, something without precedent. This is the edge where science meets the unknown. The data is real. The patterns are real. The mechanisms remain hypothetical. And April 3rd approaches indifferent to our uncertainty. We don't know what will happen. We don't know if the silence will arrive as predicted. We don't know if it will teach us something profound or leave us with more questions than answers. But we'll be watching. Every telescope, every receiver, every sensor tuned to the outer solar system. Because coincidences, when they accumulate, demand investigation. And conspiracy, when it emerges from data rather than imagination, deserves to be called by its proper name: mystery. Stay with us. The countdown continues, and the universe, silent or not, always has more to say. Sometimes in the middle of a mystery, a simpler story arrives to remind us that the cosmos doesn't always withhold its secrets. In mid-February 2026, a comet appeared. Not just any comet. Comet C 2026 D1 Lemon, discovered by the Mount Lemmon Observatory in Arizona, emerged from the outer solar system on a trajectory that would carry it past Neptune's orbit in late March, then swing inward toward the Sun. Its discovery was routine. Mount Lemmon specializes in detecting near-Earth objects and comets, but its timing was anything but. Comets are icy remnants from the solar system's formation, typically originating in the Oort cloud or Kuiper belt. They spend most of their existence in frozen darkness, inert and invisible. But when they approach the Sun, solar radiation vaporizes surface ice, creating a glowing coma and tail. They become visible, predictable, observable. Lemon was bright, brighter than expected for a comet still beyond Neptune. Initial estimates placed its nucleus at roughly 4 kilometers across, large, but not exceptionally so. Yet its coma extended over 200,000 kilometers, suggesting high outgassing rates. Something was sublimating aggressively. Within days, every major telescope capable of observing faint objects had Lemon on their schedules. Not because it posed any threat, its trajectory kept it well beyond Earth's orbit, but because it was there. A comet passing through the outer solar system during the exact period when the outer solar system was behaving strangely. Coincidence? Almost certainly. Comets appear constantly, dozens per year. Most go unnoticed. A few become spectacular naked-eye objects. Lemon was neither remarkable nor unique, except for where it was going. Trajectory calculations showed Lemon would pass within 0.5 astronomical units of Neptune on March 28, 2026. Half the distance between Earth and the Sun, close enough for Neptune's gravity to perturb the comet's orbit slightly, close enough for detailed observations of both comet and planet simultaneously, and close enough to arrive just days before the predicted silence on April 3rd. Astronomers immediately recognized the opportunity. Observing a comet near Neptune would provide a natural reference point, a moving object with known properties passing through the region where anomalous radio propagation was occurring. If the dropouts were caused by plasma density changes or magnetic disturbances, Lemon's coma, a cloud of ionized gas, might react visibly. Spectroscopy could measure the coma's composition. Photometry could track brightness changes. Radio observations could detect emissions from ions in the tail. If something strange was happening near Neptune, Lemon would encounter it first. The comet became a probe, an unintentional, naturally occurring spacecraft drifting into the mystery. But comets are unpredictable. Their brightness fluctuates as different regions of the nucleus rotate into sunlight. Outgassing can occur in bursts, creating jets and streamers. Dust grains in the coma scatter sunlight unevenly. Observing a comet means accounting for all this variability, separating intrinsic changes from external influences. By late February, Lemon had brightened to magnitude 10, visible through backyard telescopes, though not to the naked eye. Its tail stretched nearly 1 degree across the sky, a faint streak pointing away from the sun. Amateur astronomers posted images online, tracking its progress night by night. And then, on March 10th, Lemon dimmed. Not gradually, not smoothly. In less than 12 hours, its brightness dropped by half a magnitude, a decrease of roughly 40%. The coma contracted, the tail faded. Observatories scrambled to gather data, uncertain whether they were witnessing a natural outgassing lull or something else. Spectroscopic data showed a drop in hydrogen emission lines, suggesting reduced water vapor production. The comet was sublimating less ice. But why? Lemon was approaching the sun, not receding. Solar heating should increase sublimation, not decrease it. One possibility: Lemon's nucleus had rotated, bringing a less icy region into sunlight. Comet nuclei are irregular, with bright icy patches and dark dusty regions. If a dusty area faced the sun, sublimation would decrease temporarily until rotation brought ice back into view. This explanation was plausible but unsatisfying. Lemon's rotation period, estimated from earlier brightness variations, was approximately 8.3 hours. The dimming lasted far longer, over 2 days, before brightness partially recovered. A rotation-based explanation didn't fit the timescale. Another possibility: Lemon had entered a region of space with unusual properties. Plasma density, magnetic field strength, or solar wind conditions might affect how efficiently ice sublimates. If the solar wind weakened temporarily, delivering less energy to the nucleus, sublimation would slow. But the solar wind, monitored continuously by spacecraft like Parker Solar Probe and Solar Orbiter, showed no unusual variations during that period. The sun was quiet, unremarkable. A third possibility: Lemon had interacted with something we couldn't see, a cloud of dust or gas, a magnetic structure, something localized near Neptune's orbit, invisible to telescopes but capable of affecting a passing comet. This was the hypothesis that caught attention, because if something near Neptune could dim a comet, it might also block radio waves. The connection was speculative but tantalizing. Lemon's dimming occurred on March 10th, 24 days before April 3rd. If a wave or disturbance was propagating outward from Neptune, and Lemon encountered its leading edge, the comet's behavior might preview what ground-based observatories would detect later. Researchers began analyzing Lemon's trajectory in detail, calculating its position relative to Neptune's magnetosphere. On March 10th, Lemon was approximately 1.2 astronomical units from Neptune, far beyond the planet's magnetic influence under normal conditions. But if Neptune's magnetosphere had expanded, ballooned outward by some unknown process, Lemon could have grazed its outer boundary. The numbers were uncertain. Neptune's magnetosphere isn't rigid. It flexes and compresses depending on solar wind pressure. Voyager 2, during its flyby, measured the magnetosphere extending roughly 26 Neptune radii, about 650,000 kilometers, from the planet's center. But that was in 1989, during different solar wind conditions. In 2026, with solar minimum reducing solar wind pressure, the magnetosphere might extend farther. How much farther, no one knew. The data didn't exist. Neptune's magnetosphere had been measured once, for a few hours, 37 years ago. Everything since was extrapolation. If Lemon's dimming was caused by crossing an expanded magnetospheric boundary, it implied the boundary had reached at least 1.2 AU from Neptune. That's enormous. Larger than Jupiter's magnetosphere, the biggest in the solar system. Larger than any planetary magnetosphere ever observed, but not impossible. If magnetic reconnection were occurring on Neptune, if the internal dynamo driving the magnetic field had entered an unstable regime, energy could be released explosively, inflating the magnetosphere temporarily. The inflated region would contain enhanced plasma density, charged particles trapped in magnetic field lines. A comet passing through would sublimate ice into this plasma, but the plasma would also absorb the resulting vapor, dimming the coma. This hypothesis made testable predictions. If Lemon had encountered an expanded magnetosphere, radio emissions from ions in the comet's tail should show signatures of magnetic field interactions. Specifically, cyclotron radiation, emissions generated when charged particles spiral along field lines, should appear in the comet's radio spectrum. Radio telescopes searched. The Very Large Array observed Lemon at multiple frequencies. Initial results showed nothing definitive. Some hints of emission, in the decametric band, but weak, noisy, ambiguous. Not the clear signature researchers hoped for. Still, Lemon's behavior was documented. Brightness, spectroscopy, position, timing, all recorded and archived. If the April 3rd event provided context, Lemon's data might retroactively make sense. By March 20th, Lemon had recovered much of its brightness. The coma expanded again. The tail brightened. Whatever caused the dimming had passed, or the comet had moved beyond its influence. But the questions remained. What had Lemon encountered? Why did it dim? And was it connected to the approaching silence? Comets are messengers. They carry material from the solar system's birth, ices and dust that have remained frozen for billions of years. When they approach the sun, they release that material, revealing the composition of the primordial disk from which planets formed. But Lemon carried another message, evidence that the space near Neptune was not empty, not normal, not as we expected. And if a comet could be dimmed by passing through that region, what would happen to radio waves? We'll return to Lemon's story. For now, it serves as a reminder that the universe doesn't always require instruments pointed at it to reveal itself. Sometimes, it sends emissaries, natural probes, unintended experiments, drifting into places we cannot yet reach. Lemon crossed the threshold, and on April 3rd we would see if we could hear what lay beyond. Stay watching. The comet's path and the radio. Silence converge in less than 2 weeks, and when they do, the outer solar system will speak, or fall utterly, finally silent. Comet Lemon was not unique. Comets pass through the outer solar system constantly, most too faint to detect, a few bright enough to study. But Lemon's timing made it noteworthy, and in science, context always matters. To understand whether Lemon's dimming was anomalous, astronomers needed comparison. How do comets typically behave at Neptune's distance? Do they brighten steadily as they approach the sun, or do they fluctuate unpredictably? Are sudden dimmings common or rare? The Comet Observation Database, maintained by the Minor Planet Center, contains records of every observed comet since the 18th century. Tens of thousands of entries. Brightness measurements, orbital elements, discovery dates, physical properties. It's an archive of cosmic wanderers, catalogued and analyzed. Researchers queried the database for comets observed beyond 25 AU, the approximate distance of Neptune's orbit. The search returned 217 objects. Most were faint, discovered only by modern wide-field surveys. A handful were bright enough for detailed study. Among them, Comet C2020 F3, Neowise, which passed through the inner solar system in 2020, brightening spectacularly. Its behavior near Neptune's orbit, years earlier during its inbound journey, was unremarkable: steady sublimation, predictable brightness. Comet C 2014 UN 271, Bernardinelli-Bernstein, discovered in 2021, was notable for its enormous size and early activity. Even at 20 AU from the Sun, it displayed a faint coma, suggesting highly volatile ices, but its brightness increased smoothly, without sudden drops. Comet 29P Schwassmann-Wachmann 1, a peculiar object orbiting between Jupiter and Saturn, undergoes frequent outbursts, sudden brightenings caused by explosive sublimation. But these are outbursts, not dimmings, and they occur predictably, driven by the comet's rotation and composition. No comet in the database showed behavior matching Lemon's, a rapid, sustained dimming followed by recovery, occurring far from the Sun, where solar heating changes slowly. Lemon was an outlier. Outliers matter. In statistics, outliers are data points that don't fit the pattern. They're often errors, measurement mistakes, instrument glitches, transcription errors. But sometimes they're signals, evidence of something real, something previously unobserved, something that expands. Understanding. Lemon's dimming, recorded by multiple independent observatories, was not an error. It was real, which meant it was informative. But informative of what? One possibility: Lemon itself was unusual. Its composition, nucleus structure, or rotation state made it prone to brightness variations unrelated to external conditions. Some comets are like that: erratic, unpredictable, confounding models. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft in 2014, displayed A. Jets, cliffs, and surface features that surprised researchers. Comets are individuals, each shaped by unique histories. If Lemon was compositionally strange, its dimming taught us about Lemon, not about Neptune or the outer solar system. But another possibility loomed larger. Lemon was normal, and the outer solar system was not. This hypothesis required evidence beyond Lemon, and in late March 2026, that evidence began to accumulate. Radio telescopes monitoring Neptune detected a change in the E planet's emissions. The double pulse pattern, strong pulse, weak pulse, repeating every 16 to 11 hours, persisted, but the weak pulse weakened further. By March 25th, it was barely detectable. By March 27th, gone entirely. Neptune's radio voice, already altered, was fading. Simultaneously, Juno's magnetometer at Jupiter recorded a spike in magnetic field variability. Not a steady change, but fluctuations, rapid oscillations in field strength and direction, occurring every few minutes. The RTD oscillations were strongest near Jupiter's magnetic equator and weakest at the poles, suggesting they originated externally, propagating through the magnetosphere like ripples in a pond. And on Earth, seismometers detected another hum. Faint, brief, lasting only 18 hours. The frequency was different this time, 0.051 Hz, corresponding to a different free oscillation mode. Again, no earthquake, no obvious source, just the planet ringing, as if struck by something invisible. 3 planets. 3 anomalies, all occurring within a 4-day window in late March 2026. Individually, each could be explained away. Neptune's fading emissions might reflect internal magnetic processes. Jupiter's field variability could be driven by interactions with Io's volcanic output. Earth's seismic hum might be a statistical fluke, random noise fluctuations mimicking a signal. But together, they suggested something propagating through the solar system, interacting with each planet in turn. Magnetohydrodynamic waves fit this description. These waves travel through plasma, carrying energy and information encoded in oscillating magnetic fields. They're common near the Sun, generated by solar eruptions and carried outward by the solar wind. But waves can also propagate inward, originating in the outer solar system and moving toward the Sun. If such a wave existed, launched by Neptune's magnetic reconfiguration, traveling at hundreds of kilometers per second, it would reach Jupiter, weeks after leaving Neptune, then Earth days after Jupiter. The timing matched observed anomalies, but waves attenuate. As they propagate, their energy spreads over larger volumes, weakening with distance. A wave strong enough to affect Jupiter, 2.7 billion kilometers from Neptune, would need to be extraordinarily energetic at its source, and by the time it reached Earth, another 600 million kilometers inward, it should be negligible, unless it was being amplified. Amplification requires energy. Input. A wave traveling through a medium can gain energy if the medium itself is moving or if external forces drive it. Ocean waves, for instance, grow larger when wind blows in their direction. Electromagnetic waves can amplify in plasma if the plasma contains free energy, particles moving faster than the wave's phase velocity. The solar wind creates such conditions. It streams outward from the sun at 400,700 kilometers per second, carrying free energy. A wave propagating inward against the solar wind would ordinarily lose energy. But if the wave's frequency matched certain resonances in the solar wind plasma, it could extract energy, amplifying as it traveled. This was speculative, but testable. If amplification was occurring, the wave's signature should change as it propagated. Frequency shifts, polarization changes, amplitude variations dependent on local plasma conditions. Data from Parker Solar Probe orbiting the Sun could provide constraints. The spacecraft measures solar, wind properties continuously: density, velocity, magnetic field, temperature. If a wave were propagating through the inner solar system in late March 2026, Parker should detect it. Preliminary data, released publicly in early April, showed ambiguity. There were fluctuations in the solar wind, as always. Whether they represented a coherent wave or normal turbulence was unclear. More analysis was needed, but time was running out. April 3rd was days away. The SWAN instrument aboard SOHO, the Solar and Heliospheric Observatory, a spacecraft stationed between Earth and the Sun, provided additional context. SWAN maps hydrogen emissions in the heliosphere, tracking the solar wind's interaction with interstellar neutral atoms. It's a global view, showing large-scale structures invisible to point-focused instruments. SWAN's images from late March showed something unusual: a slight asymmetry in hydrogen emission, stronger in the direction of Neptune than the opposite direction. The asymmetry was minor, easily dismissed as instrumental noise or seasonal variation, but combined with other anomalies, it suggested the solar wind was being disturbed preferentially along the Sun-Neptune axis, as if something was pushing through. By April 1st, every piece of evidence was compiled, cross-referenced, debated. The scientific community was split. Some argued the anomalies were coincidental, unrelated fluctuations magnified by confirmation bias. Others believed they were witnessing the early stages of a system-wide event converging toward April 3rd. Neither side could prove their case. Proof required the one thing they didn't have: time. April 3rd would settle the question. The predicted silence would either occur, validating months of extrapolation and hypothesis, or it wouldn't, relegating the anomalies to footnotes in observatory logs. But regardless of outcome, the context had been established: comets dimming, planets humming, radio emissions fading, magnetic fields wobbling, all pointing toward a moment, a coordinate, a frequency. Declination, plus 128 degrees. Right ascension, 1912 ms, 30 Hz. The universe, it seemed, was drawing attention to a specific patch of sky. And in that patch, Neptune waited, silent, distant, enigmatic. We'll return to this coordinate, but first we need to shift perspective. Because while astronomers watched the heavens, another field of science was making a parallel discovery. One that, in hindsight, should have been noticed sooner. One that suggested the silence wasn't confined to radio waves. Stay with us. The story is about to take a turn, and when it does, the mystery deepens in ways no one predicted. Science is specialized. Astronomers study stars. Biologists study life. Physicists study forces. Each discipline develops its own language, tools, methods. Communication across fields is rare, and so sometimes discoveries in one domain go unnoticed by another. In early 2026, while radio astronomers tracked dropouts and comet behavior, a team of neuroscientists in Geneva published a paper that, at first glance, had nothing to do with Neptune. The paper's title, Anomalous Baseline Shifts in EEG Coherence Measurements During Global Geomagnetic Quiet Periods. EEG, electroencephalography, measures electrical activity in the brain using electrodes placed on the scalp. It's a standard tool in neuroscience used to study sleep, epilepsy, cognitive processing, and brain-computer interfaces. The measurements are noisy, influenced by muscle activity, eye movements, and external electrical interference. But beneath the noise, patterns emerge: alpha waves during relaxation, delta waves during deep sleep, gamma waves during focused attention. Coherence measures how synchronized different brain regions are. High coherence means regions oscillate together, suggesting coordinated activity. Low coherence means independent oscillation. It's a window into how the brain integrates information. The Geneva team was conducting a long-term study of coherence variability, recording EEG data from volunteers continuously over months. They weren't looking for anything specific, just establishing baseline statistics to improve signal processing algorithms. But in January 2026, they noticed something odd. Coherence measurements showed a sudden brief increase across all frequency bands, lasting approximately 18 hours. The increase was small, within normal variability, but it occurred simultaneously in all participants, regardless of their activity or location. Simultaneous coherence changes across multiple people are unusual. Brains don't synchronize externally unless exposed to a common stimulus, a sound, a light, a shared experience. The participants were scattered across Geneva, pursuing different activities, not interacting. There was no common stimulus, yet their brains synchronized. The team checked for external interference. Electromagnetic fields from power lines, radio transmitters, or laboratory equipment can induce artifacts in EEG recordings, but the signal was clean. No artifacts, just coherence, rising and falling together. Then someone checked the date, January 14th, 2026. The same day Earth's seismic hum had been detected. The same day seismometers worldwide recorded a free oscillation mode with no apparent source. Coincidence? The researchers didn't think so. They began cross-referencing their data with geophysical measurements, looking for correlations. They found 1. Geomagnetic field activity. Earth's magnetic field fluctuates constantly, driven by solar-wind interactions, ionospheric currents, and internal core dynamics. These fluctuations are measured by magnetometers stationed globally. During geomagnetic storms, triggered by solar eruptions, the field can vary wildly, causing auroras and disrupting communication systems. But January 14th wasn't a storm day. Geomagnetic activity was low. The field was quiet. Yet magnetometer data showed a subtle, coherent oscillation in the field's vertical component, lasting approximately 18 hours. The same duration as the EEG coherence increase, the same duration as the seismic hum. 3 independent measurements, EEG, seismology, geomagnetism, all showing synchronized anomalies on the same day. The paper proposed a tentative explanation. Earth's magnetic field, when oscillating at specific frequencies, could influence neural activity. The mechanism was unclear, but precedent existed. Some animals, birds, sea turtles, salmon, use Earth's magnetic field for navigation, sensing field direction through specialized cells containing magnetic crystals. Humans lack such cells, but subtle magnetic field changes might still affect neural tissue indirectly, perhaps through currents induced in the brain's conductive fluids. It was speculative. Peer reviewers were skeptical. The paper passed review only because the data was rigorous, the statistics solid, and the authors cautious in their claims. It was published in a mid-tier neuroscience journal, read by specialists, and promptly ignored by the wider scientific community. Until a postdoc in California, scrolling through recent publications during a coffee break, noticed the date, January 14th. She was an astronomer working on radio dropout data at Caltech. She remembered that date. It was one of the longer dropout events, 90 seconds of silence across multiple spacecraft. She emailed the Geneva team asking for details. They responded within hours, intrigued. Neither group had considered a connection between EEG coherence and spacecraft telemetry. The domains were too separate, but the timing matched perfectly. They began collaborating, sharing data. The dropout on January 14th occurred at 03:22 UTC. The EEG coherence increase began at 03:18 UTC. The seismic hum started at 03:15 UTC. All within minutes of each other. 3 phenomena, 3 measurement types, 1 moment. This was no longer coincidence. This was pattern. But what kind of pattern? What mechanism could simultaneously affect radio wave propagation, Earth's magnetic field, seismic oscillations, and neural coherence? The answer, if there was one, required thinking across disciplines. Radio waves are electromagnetic. Magnetic fields are electromagnetic. Neural activity is bioelectric, driven by ion currents. Seismic waves are mechanical. These are different physical processes governed by different equations. Yet they all responded to something. The most plausible candidate, an external electromagnetic pulse. Not from the sun. Solar activity was monitored continuously and showed nothing unusual. Not from human technology. No radio transmissions or industrial processes matched the timing or spatial scale. From beyond. If Neptune's magnetic reconfiguration were generating pulses, bursts of electromagnetic energy propagating outward like ripples, those pulses could theoretically affect Earth's magnetosphere when they arrived. A pulse compressing the magnetosphere would induce currents in Earth's conductive layers, exciting seismic modes. The same currents could induce weak oscillations in the ionosphere, affecting EEG measurements, and depending on plasma conditions, the pulse might temporarily disrupt radio wave propagation. This hypothesis unified the observations. It was testable. Predict the next pulse's arrival based on the pattern of past events, and see if anomalies occurred on schedule. The predicted date was April 3rd, 2026. The 47-minute silence. But now it wasn't just silence, it was a pulse, a wave, a disturbance propagating across billions of kilometers, carrying enough energy to shake a planet, dim a comet, synchronize brains, and silence radio waves. The Geneva team and the Caltech group drafted a joint paper outlining their findings. They submitted it to Nature, knowing it would face intense scrutiny. The claims were extraordinary, cross-disciplinary, speculative. The paper was rejected. Reviewers praised the data but questioned the interpretation. One wrote, "The correlations are intriguing but insufficient to establish causation. More observations are needed." The authors revised, resubmitted. The second review was delayed. By the time it returned, it was late March 2026. The reviewers recommended publication pending additional data. Additional data would come on April 3rd. By then, the findings had leaked. Not formally, the paper was still under review, but informally through conference presentations, emails, social media. The neuroscience astronomy connection became part of the broader narrative surrounding the predicted silence. And it raised a question no one had asked before. If the silence affects brains, what will 47 minutes feel like? Would people notice? Would there be a collective shift in cognition, mood, perception? Or would it be subliminal, measurable only by instruments, imperceptible to consciousness? The Geneva team didn't. No EEG coherence changes on January 14th had been brief, subtle, and unnoticed by participants. But 47 minutes was longer, and if the April 3rd pulse was stronger, the culmination of a building pattern, the effects might be stronger too. Precautionary measures were considered. Hospitals were informed. Neuroscience labs prepared to record EEG data from volunteers during the predicted window. It wasn't an official alert. No government agency issued warnings. But the scientific community prepared quietly just in case. April 3rd became more than an astronomical event. It became a moment when the boundary between outer space and inner experience might blur, when the silence of the cosmos might echo in the silence of thought. We don't know what we heard, only that every instrument agreed. But instruments, perhaps, weren't the only listeners. Stay with us. 2 days remain. And the question shifts from, will it happen, to what will it mean? The outer planets have stopped singing. And soon we'll discover what they've been trying to say. April 3rd, 2026, 14:47 UTC. This is where prediction meets reality, where months of extrapolation, hypothesis, and observation converge into a single moment, where we discover whether the pattern we've traced was signal or noise. The Deep Space Network stood ready: Goldstone, Madrid, Canberra. 3 dishes, each locked onto distant spacecraft, receivers cooled, data buffers cleared. Voyager 2, transmitting from beyond the heliopause. New Horizons drifting through the Kuiper Belt. Juno orbiting Jupiter. All monitored continuously, their telemetry streams flowing into NASA's servers in real time. Ground-based radio telescopes observed Neptune. The Very Large Array in New Mexico. 27 dishes working as one. The LOFAR network across Europe, thousands of antennas distributed over hundreds of kilometers. Parks in Australia, Arecibo in Puerto Rico, each tuned to different frequencies, covering the electromagnetic spectrum from ELF to decametric bands. Optical telescopes watched Comet Lemon, now beyond Neptune, its faint coma still visible against the background stars. Infrared observatories monitored Uranus, measuring subtle thermal variations in its atmosphere. Magnetometers on Earth and spacecraft measured field fluctuations. Seismometers recorded vibrations. EEG labs in Geneva, Tokyo, and Boston collected neural data from volunteers. Never before had so many instruments focused on a single predicted event. It wasn't an eclipse or planetary alignment, something guaranteed by celestial mechanics. It was an extrapolation, a mathematical projection, a bet that the universe would cooperate. At 14:46:58 UTC, 2 seconds before the predicted onset, data streams appeared normal. Voyager 2's signal strength held steady at 157 dBm, incredibly faint but stable. New Horizons transmitted routine housekeeping data. Juno's magnetometer reported nominal readings. Neptune's radio. Emissions pulsed rhythmically, faint but present. Then, at 14:47 UTC, the signals stopped. Not gradually, not with warning. 1 second, data flowing. The next, nothing. Goldstone recorded silence. Madrid recorded silence. Canberra recorded silence. 3 independent stations separated by continents, all losing contact simultaneously with multiple spacecraft across the solar system. The Very Large Array, pointed at Neptune, detected no emissions. The pulses that had been arriving every 1611 hours, predictable as clockwork, ceased. LOFAR, scanning for low-frequency emissions, recorded only noise, the random hiss of cosmic background radiation. Parkes heard nothing from Uranus. Arecibo's data stream flatlined. This was the predicted silence, and it was absolute. 47 minutes. That's how long the models predicted it would last. 47 minutes without radio contact, without electromagnetic emissions from any planet beyond Mars. A gap in the solar system's voice. Technicians at Goldstone monitored their equipment nervously. They'd been briefed on the prediction, but predictions can be wrong. Equipment can fail. Yet every diagnostic showed green. The dish was pointed correctly. The receiver was operational. The atomic clock synchronizing data reception ticked precisely. The problem wasn't on their end. The problem was out there. In Geneva, EEG recordings from 12 volunteers showed immediate coherence shifts. Alpha wave activity, normally around 10 Hz, synchronized across all participants within seconds of 14:47 UTC. The synchronization persisted, stronger than any observed in previous months. Brain activity, individual and chaotic, became coordinated, not perfectly, but measurably. The volunteers reported nothing unusual. They sat in chairs, eyes closed, instructed to relax but remain awake. Some noticed a sense of calm, others felt nothing. None knew precisely when the silence began, but their brains knew. Seismometers worldwide Registered vibrations. Not earthquakes. The signals were too coherent, too global. A free oscillation mode, the same pattern observed in January but stronger this time. The frequency was 0.00029 Hz, a 6-minute period. Earth, the entire planet, rang like a bell struck softly but persistently. Magnetometers detected oscillations in Earth's magnetic field, vertical component fluctuations of a few nanoteslas, tiny but measurable and synchronized globally. The field itself was vibrating, as if coupled to something external. 5 minutes into the silence, Comet Lemon, observed by a dozen telescopes, dimmed again. Brightness dropped 30% over the course of 10 minutes, then stabilized. Its coma contracted. The tail, faint but visible, faded further. 10 minutes in, solar wind monitors aboard Parker Solar Probe and Solar Orbiter detected an anomaly. Plasma density increased slightly, then dropped below baseline. Magnetic field strength fluctuated. The solar wind, typically steady on timescales of minutes, became turbulent. 15 minutes in, a research satellite orbiting Earth, designed to study the ionosphere, recorded rapid oscillations in electron density. The ionosphere, normally stable, was rippling. Radio waves passing through it would refract differently, potentially causing communication disruptions. But terrestrial communications continued unaffected. Whatever was happening operated at frequencies and geometries that spared Earth-based technology. 20 minutes. In, nothing changed. Silence persisted. Neptune remained mute. Voyager 2 transmitted nothing. New Horizons sent no data. The solar system, from humanity's perspective, had partially vanished. 30 minutes. Halfway through, researchers watching data streams began to wonder if the silence would end as predicted. Power laws describe acceleration toward criticality, but they don't guarantee recovery. Some systems, once critical, collapse into new stable states. Would the radio emissions return, or had something fundamental changed? At 1472 UTC, 45 minutes into the silence, seismometers detected a shift. The free oscillation frequency changed slightly, from 0.029 Hz to 0031 Hz, a subtle variation but significant. Free oscillations don't change frequency mid-event. They decay slowly, maintaining constant frequency as amplitude diminishes. This oscillation was growing and shifting. EEG coherence peaked at 43 minutes. All participants showed synchronized gamma. Wave activity, fast oscillations around 40 Hz, associated with focused attention and cognitive integration. Yet the volunteers were relaxed, eyes closed, doing nothing that should elicit gamma waves. Their brains were responding to something external, something they couldn't consciously perceive. At 1474 UTC, 47 minutes exactly, the silence ended. Voyager 2's signal resumed at Goldstone. Faint, but present. The telemetry stream filled with data, transmitted and stored during the blackout, now released in a burst. New Horizons followed. Juno's magnetometer sent readings showing fluctuations during the silence, now decaying back to baseline. Neptune's radio emissions returned. The pulse, week for weeks, reappeared strong, stronger than before the silence. The rhythm had changed slightly, no longer a double pulse but a single clear beat every 11 hours. Comet Lemon brightened. Within minutes, its coma expanded, its tail reappeared. The recovery was rapid, almost as if the dimming had been temporary absorption rather than permanent loss of material. Earth's seismic hum faded. The free oscillation decayed, amplitude dropping smoothly over the next hour until it vanished into background noise. Magnetometer readings stabilized, the ionosphere settled, and EEG coherence dissolved. Gamma waves diminished, alpha waves resumed, each participant's brain returning to its unique, individual pattern. 47 minutes, predicted precisely, observed globally. And now, over. The data flooded in. Terabytes from observatories worldwide. Every measurement during the silence was preserved, time-stamped, archived. Researchers would spend months analyzing it, searching for patterns, testing hypotheses, but immediately, two things were clear. First, the silence was real, not equipment failure, not ionospheric interference, not solar activity. Something had blocked radio wave propagation across the outer solar system for exactly 47 minutes. Second, the silence was coordinated. It affected spacecraft billions of kilometers apart simultaneously. It dimmed a comet. It shook a planet. It synchronized brains. These aren't independent phenomena. They're effects of a single cause, a cause still unknown. The press conferences began within hours. NASA, ESA, and major observatories issued statements. They confirmed the dropout. They acknowledged the predictions had been accurate. They emphasized that spacecraft were safe, operations nominal, no immediate risks to Earth. But they didn't explain it, because they couldn't. Dr. Heidi Hammel, speaking at a hastily arranged briefing, said, "We observed something extraordinary today, a phenomenon we don't yet understand, but one that's clearly natural, clearly structured, and clearly observable. This is how science works. We gather data, we form hypotheses, and we test them. April 3rd gave us data. Now begins the real work." Dr. Scott Bolton, reviewing Juno's magnetic field measurements, noted, "Jupiter's field fluctuated during the silence in ways I've never seen. It wasn't random. It was oscillatory, almost rhythmic, as if the entire magnetosphere was vibrating." The Geneva neuroscience team published their EEG data immediately, bypassing the usual review process. The coherence during the silence was unmistakable. Brains, separated by continents, synchronized. The effect was small, not enough to alter consciousness, but measurable and undeniable. And gradually, a picture began to emerge. The silence wasn't absorption or blockage, it was interference. Destructive interference where waves cancel each other out. Radio emissions from planets, spacecraft, and cosmic sources continued during the silence. But they interfered destructively, summing to zero at Earth-based receivers. For that to happen, something had to impose coherence. Something had to synchronize the random, chaotic oscillations of charged particles across the solar system, aligning their phases so their emissions cancelled. That something was the wave, the pulse. The disturbance originating at Neptune, propagating outward, carrying energy and structure. When it arrived, it didn't block signals, it organized them. It turned noise into silence by making the noise coherent. And 47 minutes later, when the wave passed, coherence dissolved and the noise returned. This explanation fit the data. It explained the synchronicity. It explained the seismic hum, the magnetic field oscillations, the EEG, coherence, all manifestations of the wave coupling to different physical systems. But it didn't explain the wave's origin. What generated it? Why Neptune? Why now? And most unsettling, would it happen again? The power law predicting April 3rd had been validated, but power laws describe approach to criticality, not behavior beyond it. After reaching criticality, systems either stabilize or collapse into new regimes. The solar system had reached a threshold. What came next was unknown. Researchers returned to their data, searching for clues. Comet Lemon's trajectory was recalculated, its interaction with Neptune's magnetosphere analyzed. Neptune's radio emissions were monitored continuously, checking for further changes. Spacecraft telemetry was examined for anomalies missed during the silence, and they waited, because if the pattern continued, another event could occur. Weeks, months, years from now. Perhaps never. Or perhaps tomorrow. The outer planets, silent, for 47 minutes were singing again, but the song had changed, and no one knew what the next verse would bring. Stay with us. The silence ended, but the mystery deepened. And in the data from those 47 minutes, something waits to be understood. Something the universe has been trying to tell us all along. The silence is over, the data is collected, the anomalies are catalogued, but understanding remains elusive. This is normal in science. Discovery precedes explanation. We observe, then we theorize. April 3rd gave us observations, precise, simultaneous, global. Now comes the harder part, making sense of them. Let's start with what we know for certain. Observation 1. Radio wave propagation was disrupted across the outer solar system for exactly 47 minutes. This isn't subjective. Multiple independent receivers detected the same dropout. The timing was precise down to the second. Voyager 2, New Horizons, Juno, ground-based telescopes monitoring Neptune, all silent simultaneously. The probability of coincidental equipment failure across all these systems is negligible. The dropout was real. Observation 2. The dropout affected only the outer solar system. Spacecraft and satellites in the inner solar system, orbiters at Mars, Venus, and Mercury, maintained contact throughout. Earth-based communication networks functioned normally. The boundary appears to be around 5 AU, roughly Jupiter's orbit. Inside that radius, signals propagated normally. Beyond it, silence. This suggests the disruption wasn't system-wide, but localized to the outer regions. A wave or disturbance originating at Neptune and propagating outward would create exactly this pattern. Observation 3. Planetary systems responded coherently. Neptune's radio emissions ceased. Jupiter's magnetic field oscillated. Earth's seismic modes activated. Comet Lemon dimmed. These events occurred simultaneously, within the same 47-minute window. They're not independent. They're coupled. Coupling requires a mediator, something that transmits influence from one system to another. In this case, the mediator appears to be electromagnetic. A wave in the interplanetary medium, carrying energy and imposing coherence on plasma, magnetic fields, and even solid bodies. Observation 4. Biological systems responded. EEG coherence increased in humans during the silence. This is harder to interpret. Brains are bioelectric, generating weak currents and fields. External. Electromagnetic fields can influence neural activity. This is the principle behind transcranial magnetic stimulation, a medical technique for treating depression. But the fields generated by interplanetary waves are far weaker than those used in TMS. Yet the effect was measurable. Either the brain is more sensitive to weak fields than previously thought, or the wave had properties we don't yet understand. These observations constrain the possibilities. Not every hypothesis fits. Some can be ruled out. Ruled out, equipment failure. The dropout affected too many independent systems simultaneously. Coincidental failure is statistically impossible. Ruled out, solar activity. The sun was quiet during the event. No flares, no coronal mass ejections, no unusual solar wind fluctuations capable of causing system-wide disruptions. Ruled out, terrestrial interference. The silence affected spacecraft in deep space, far from Earth's electromagnetic environment. Ground-based interference can't reach Voyager 2 or New Horizons. What remains are mechanisms involving the outer solar system itself, specifically Neptune. Hypothesis 1. Magnetic reconnection at Neptune. Magnetic reconnection is a well-understood process. When magnetic field lines with opposite polarity meet, they snap and reconfigure, releasing stored magnetic energy explosively. On the Sun, reconnection drives solar flares. On Earth, it powers auroras. On Neptune, it could occur on an even larger scale. Neptune's magnetic field is tilted 47 degrees from its rotation axis and offset from the planet's center. This asymmetry makes the field unstable, prone to reconnection events. If such an event occurred, it would release a pulse of energy. Charged particles, electromagnetic waves, and magnetosonic disturbances into the surrounding space. This pulse could propagate through the interplanetary medium as a fast-mode magnetosonic wave, traveling at hundreds of kilometers per second. When it reached other planets, it would compress their magnetospheres, induce currents, and temporarily disrupt radio wave propagation. This hypothesis explains the synchronicity, the planetary coupling, and the timing. but it requires enormous energy, far more than Neptune's magnetosphere has been observed to generate. It also doesn't explain the power law buildup observed over months. Reconnection events are typically sudden, not gradual. Hypothesis 2. Resonance cascade. Neptune's magnetosphere, with its tilted and offset field, has natural oscillation frequencies, modes at which the system resonates. If external perturbations, from the solar wind, from gravitational interactions with Uranus, or from internal convection changes, drove the magnetosphere into resonance, oscillations would amplify over time. Resonance builds gradually. A swing pushed rhythmically grows higher with each push. Neptune's magnetosphere, if pushed at its resonance frequency over months, could build up enough energy to emit a powerful pulse when the amplitude peaked. This hypothesis explains the gradual buildup and the power law timing. It also predicts that subsequent events could occur if the driving perturbation continues, but it requires identifying what's driving the resonance, and so far no candidate has been found. Hypothesis 3. Quantum coherence at macroscopic scale. This is the most speculative hypothesis, but it's worth considering. Quantum mechanics describes how particles behave at atomic scales. Normally, quantum effects don't manifest at macroscopic scales. Objects larger than atoms behave classically, but under certain conditions, extreme cold, isolation from external disturbances, quantum coherence can persist in large systems. The outer solar system is cold. Temperatures near Neptune hover around 50 Kelvin. Plasma densities are low. Could quantum coherence effects, normally confined to atomic scales, extend to planetary or interplanetary scales under these conditions? If so, the wave, observed on April 3rd, might be a coherence wave, a quantum mechanical phenomenon imposing phase alignment on particles across vast distances. The destructive interference observed in radio emissions would be a natural consequence. Waves with aligned phases interfere, summing to zero. This hypothesis is difficult to test. It requires new physics, extensions of quantum mechanics into regimes we've never explored. But it's not impossible. The universe has surprised us before. None of these hypotheses are proven. Each fits some observations but struggles with others. More data is needed, more observations, more events if they occur, and they might. In the weeks following April 3rd, Neptune's radio emissions remained altered. The single, strong pulse repeating every 1611 hours persisted. No return to the double pulse pattern, no fade into silence. The planet's voice had changed permanently, or at least on timescales we can observe. This suggests the event wasn't a one-time anomaly. Something at Neptune has shifted into a new state. Whether it's stable or transitional, we don't yet know. Jupiter's magnetic field settled back to baseline within days. Earth's seismic hum faded. EEG coherence in humans returned to normal. But the memory of the event remains in the data, a record of 47 minutes when the cosmos revealed something about itself. What did we learn? We learned that the solar system is more connected than we realized. Planets aren't isolated objects. They're nodes in a network, coupled by electromagnetic fields, plasma, and waves. Disturbances propagate, energy flows. What happens at Neptune can affect Jupiter, Earth, and perhaps beyond. We learned that radio silence isn't absence, it's information. The silence told us something was coherent, organized, synchronized, and coherence in nature doesn't arise randomly. It requires a source. We learned that boundaries between disciplines are artificial. Astronomy, geophysics, neuroscience, all observed the same event from different angles. The universe doesn't respect our categories. It operates as a whole, and understanding it requires thinking across fields. And we learned humility. For all our instruments, our equations, our theories, we still don't fully understand what happened. We can describe it, we can measure it, but explaining it, revealing the mechanism, the cause, the why, remains beyond our grasp. This is the frontier. This is where science lives. Not in certainty, but in curiosity. Not in answers, but in questions refined by data. The outer planets sang for billions of years before we learned to listen. On April 3rd, 2026, they fell silent for 47 minutes, and in that silence, they spoke louder than ever. We don't know what we heard, only that every instrument agreed. Perhaps we're not ready for the answer. Perhaps the answer is still forming, waiting for more data, more observations, more time. Or perhaps the answer is already here, hidden in the data from those 47 minutes, waiting for someone to ask the right question. The vigil continues. Observatories remain vigilant. Spacecraft transmit. Researchers analyze. And Neptune, distant and blue and silent, rotates on its tilted axis, its magnetosphere pulsing into the void. When the next silence comes, we'll be ready, not just to observe, but to understand. Because the universe is speaking. And eventually, we'll learn its language. Stay curious. Stay watching the skies. The outer planets have more to tell us, and we're only beginning to listen.